a choice right now, between fear and love. It's just a rock.
Out of the dark night of ignorance and into the shining light of truth.
Expanding reality.
A population of citizens capable of critical thinking.
We don't see things as they are, we see them as we are.
There's a level of reality where everything dissolves into an ocean of energy.
We empower our experience by insisting on our authenticity.
That's very profound. Very.
Expanding reality.
Welcome to Expanding Reality. I am your host, Brandon Thomas. This week we are very excited to re-invite Mr. Curt Carlton. He was the Boeing employee contracted out through NASA. Last week we covered a bunch of really cool stuff that you did, man. From the space shuttle program, from all sorts of different engineering challenges that you encounter, to just basically having the most awesome job I've ever heard of in my life. So that's pretty cool. And of course, back with us is Patrick. How you doing, Patrick?
I'm doing great.
Cool. Okay. Well, welcome to Expanding Reality, guys. Thank you all so much for listening. And you can always hit us up at expandingrealitypodcast@gmail.com. You can find us at the Instagram, the Facebook, the Twitter, all those good things. The video of this will be up on our Expanding Reality YouTube. So if you want to see what this handsome man, Curt Carlton, looks like, as well as my handsome brother, Patrick, then you can. So that's where you can do that. So let's pick this thing back up where we left off last time that we were speaking, which was your job is super awesome. And you did a bunch of really cool stuff through your career. So one thing I was curious about were all the testing facilities. So what did that involve?
One of the great things about working with NASA is that NASA has all the test facilities. I mean, that's they have vacuum chambers, thermal vacuum chambers, arc jet facilities, the Neutral Buoyancy Lab, the Comet, the zero gravity aircraft.
Yes.
When they contract you for a job, you can utilize their facilities to certify whatever they've asked you to do. Yeah. So that gives you just a huge ability to do some very cool things. I mean, I was a scuba diver in the Neutral Buoyancy Lab. I flew in numerous missions on the Comet, and all of those are to test aspects of the designs you're trying to get, you're selling to NASA.
Yeah.
And it was either parts of Space Shuttle or parts of Space Station, and they're all just very cool, one of a kind designs. So you have to go through a certification process for that design, and you're using their test facilities to prove that what you designed will work.
Because those elements of the testing facilities are already certified, and those are the requirements to be able to certify anything that gets shot into space based on those test facilities.
Correct. And we there's a huge amount. My late career was involved with making sure anything that we designed that an astronaut had to touch, assemble, manipulate, actuate, that it was properly designed. So it's designed to work with the set of tools that are available to that astronaut. Mm-hmm. It's designed to work within the capabilities of the astronaut's strength, the astronaut's vision, the actual positioning the astronaut so that he can actually do the job you're asking him to do. Yeah. So that was the later part of the job, but it was it came round full circle. Whatever you're doing that an astronaut has to touch, you've got to design properly. The hard part of it, and I was talking with Patrick earlier, the boring part of the job is working the requirements and working the design and trying to get to the point where you can actually have something physical and actually test it. Mm. So we would always try early to build simulators with similar mechanical interfaces so we could prove to the astronaut he could work with it. Mm-hmm. And then when you actually get to the actual flight design, you usually build a prototype that you actually put through the thermal vac testing if needed, or any of the testing needed. And again, it was working up to all the proof you had to generate before you could actually go out and build.
Right.
NASA doesn't just give you a blank check. They give you gates all the way along the line that you have to prove to them that your design is feasible, then it will actually work, and then you can actually certify it, and then we actually test it. And every gate, NASA is there to make sure that you're doing your job, and you're proving to them you're doing your job.
Yeah. What did the thermal testing involve? What was that?
NASA has all kinds. I mean, I mentioned on your last cast that it was most things you work with in the vacuum of space have to survive from minus 200F to plus 250F. Mm-hmm. So a lot of them, they have these small chambers. If you have a small thing, you can have a 3x3 chamber with, gloves reaching through it. So I can put it down to minus 200 degrees, actuate it, make sure it functions, and then heat up the changer to plus 250, reach in through the gloves again and actuate it at 250 to make sure that the mechanical aspects worked at both extremes. On a bigger scale, they have a chamber that you can actually put an astronaut into. So if I have a larger mechanism that the astronaut has to manipulate, you put that mechanism in this larger chamber, you put an astronaut in a spacesuit. Spacesuit weighs a lot. So he is suspended by a weight suspension crane.
Oh, to take the weight off of the suit in gravity.
Correct, in gravity, so that his weight and the combination weight of the suit, which is around 500 pounds.
Damn.
He doesn't have to fight that to do the testing. And then you put the mechanism in front of him and you have him actuate it. And you do the same thing. He's sitting in a chamber. Once he's in the chamber, it's not like you walk in, walk out. He stays in the chamber through the whole test. You bring things up to temperature. He walks into the chamber and he tests it. So he kind of has an airlock that he goes back into when he's not exposed to the environment. And then we change the environment and we heat everything up. And then when it's at the right test temperature, he goes back in and does it again. And you never just go at the extremes. You usually, let's just say you jump 50 degrees at a time. So you test it at ambient, and then you go 50 degree increments up to 250, and then you step it back down and you go to the cold side and you go down to, plus 20, then you go down to minus 50, and then minus 100, and actuate it at those different increments.
Makes sense.
Just to make sure it works.
Yeah. Okay, so I am definitely curious, and I know the listeners are as well, about this Vomit Comet thing. That is, of course, the airplane that goes up and does these parabolic flights, which simulate zero gravity in small increments of 30 seconds, a minute?
That's basically it. You get about a 30-second. Basically, you take an aircraft up to 30,000 feet, and you stall the aircraft. So it dives for roughly 20,000 feet, which gives you about 30-ish seconds of zero gravity effect. And it would be just like skydiving inside an airplane.
Damn.
Right. So it's very, very cool environment.
Yeah.
And to test, but that gives you a 20, 30 second window of true zero gravity.
Yeah.
So if you have an experiment that you can do in zero gravity, that is an environment you do it in. And then typically the aircraft will, we launch from Johnson Space Center or take off from Johnson Space Center, and you fly out over the Gulf. You do 20 parabolas out, and you do 20 parabolas back, and then you land at the local airfield. And that gives you, 30 seconds times 40 parabolas. So, it gives you all of 20 minutes of data to work with, and hopefully that gives you what you're looking for. We were talking earlier about the Columbia accident. One of the things that we did that was necessary, I mentioned the silica tile, it's the heat protection of the shuttle. Mm-hmm. Nothing sticks to it. So we developed several different goo applications to fill damage to these silica tiles. Right. And the zero gravity part of the job was have an astronaut apply this goo and and then he would apply it in zero gravity. So during that first 30 seconds of free fall, he applies it. And then to make sure it would set, what we would do is you go through about a 2G pullout to get back to 30,000 feet. And we set up this test stand so that the astronaut is on his back applying, a caulk gun goo over his head.
And that was your job to design the test apparatus that was mounted to the aircraft for the
Correct.
tiles.
We're implementing the test.
Right.
So we developed these. It was a file system to hold the test samples, and a test bed so the astronaut is suspended properly so that he can do the job you're asking him to do. And then we would simulate, would this stick in zero gravity? We would simulate that in the first 30 seconds. And then the proof that it actually worked is we would go through a 2G pullout. So we allow that test sample to go through a 2G pullout. And then if the goo didn't separate from the tile, we accomplished our goal.
So was this a hazing thing? Who drew the short straw for the first test run on this to lay underneath that thing as you were making sure that it tested properly?
And astronauts are usually go-to people. They're the first ones in line.
Yeah.
They're going, I want to do this.
I want to do it. If I get a black eye from this, it'll be a cool story.
And that's any test is a good test in their minds. If we're gonna get into, can we actually do this on orbit, and they can be a part of that process, they love it.
That's so cool.
And that's was the cool thing about the job was we were always testing one of a kind equipment and actually making it work.
Yeah.
Proving that it worked.
It's so cool. It's just a big science experiment the entire time. And it's fascinating. So on this particular one, you guys went out and what was your normal routine parabolic flight pattern?
Again, you go up to 30,000 feet. You dive down every minute. You dive down to 10,000 feet. You get about 30 seconds of zero gravity. The pull out and back to 30,000 feet takes about a minute and a half.
Okay.
And then as soon as you get to 30,000 feet, you're going right into the next parabola.
It's just a series deal. So you just expect it every...
Continuous parabola.
Wow.
So the job that we had was to get a test sample into the apparatus that he's testing from, go through the 2G pullout, get that test sample out, install a new fresh one, and then go for the next parabola.
Did all of them work, or did any of them fall off?
Oh, a lot of them never worked. I mean,
so they're just smacking this poor guy.
Yeah, I mean, often, you would. We tried to work techniques. It's kind of like welding. There's a technique that works best, and the same thing is true of applying a caulk.
Yeah.
Right? You got to figure out a way that is the best way to apply it without making it too gloppy. We tried to do it in layers. Could you do one thin layer and then come back and do another layer and then come back and do another layer? So a lot of times we'd reuse the samples if that worked.
So there's so much that goes into this testing stuff. It's just that even down to that, the technique. Don't just slap it on there and try it out. No, let's try this and then that. And so what were the results of that particular test? Did you guys achieve the goal that you were looking for?
Yes. And often we would take fully prepared samples that we actually applied the flight-like adhesive to, and then we would actually take that test sample and then we would put that sample into another NASA facility, which was the ArcJet facility, which simulated reentry. So
it
basically,
the heat of reentry.
you're the heat of reentry. So basically, you're applying a blowtorch into the facility, and then the pass for that test is that the goo that you applied didn't burn away or fall out as it burned away, or we would the piece in the vomit comet was to apply it. You let it cure. The next piece of the test was put it into the ArcJet and see if it burned away. And if it didn't burn away, then you have a successful test from application through reentry.
And that application process had to take place within that 30-second window of freefall. Because let's say, for instance, your chemical engineers designed a compound that would do it, but it took 32 seconds to work.
And again, we could only do as much as we could do.
Right.
So a lot of times we would prepare samples in 1G, and if you could apply it in 1G and it stuck under 1G of pullout, if you want to call it that,
sure,
just in a natural shirt sleeve environment, then you'd be okay. The tough part always got to be, okay, well, it's in a vacuum. How does the catalyst and the chemical work in a vacuum versus working in an oxygen environment? So you had to, we got to the point where we were working in a vacuum chamber and applying this goo into the tile inverted, so it had 1G of pullout, but if it stayed in with the 1G, then we could still use it and do a ablative test to see if it would stick and hold.
And that test, of course, came about because of the 2003 Columbia incident that happened whenever one of the tiles failed because of a damage on ascent, on reentry, and that's the whole reason the whole reason we even got into this set of test criteria was, again, solve the problem. How do I repair a shuttle that got hurt on ascent? Right.
And this was just one of the pieces.
That's so cool.
A completely separate company was working on the actual adhesive. And like I said, it was basically a 2-part silicon-based epoxy with a catalyst
Right.
that worked without oxygen.
Right.
Sounds simple when you roll it off the tongue like that, but it's not a simple problem.
No,
right?
it
And then that material, after it dries, has to withstand 1,000-degree reentry heat. And so typically the original, the old capsule designs, the Russians used solid oak. Their ablation shield was solid oak, because you can't burn through 3 inches of oak in a few minutes.
In that amount of time.
Right.
Yeah.
So, I mean,
Wow.
it created a char, and that char was carbon, which could take heat better than the oak itself. And you couldn't get through the 3 inches of oak, but again, you replaced it every time. It was a one-time use. Back in the capsule day, it only had to survive once.
So not only the one-time use, but probably the weight of that as well. I bet shooting that amount of wood up and then going to the silica tiles or the porcelain tiles that you guys ended up using was, because you need a lot more of those because the surface area of the shuttle.
Next time we get together, I'll bring you a piece.
Really?
Oh yeah, I have some of the silica tile, and you'll see it. It looks like it feels like styrofoam. It's so light.
Wow.
But it's actually the silica. It has a porcelain composition to it.
Damn.
And a ceramic composition to it, but it doesn't weigh anything.
Coolest job ever. I'm telling you. That's going to be the name of this episode. Coolest job ever. Oh, my apologies.
That's all right. When I graduated from school, so I went through an engineering degree, tried to focus on aircraft performance, aircraft design. That was kind of the niche I was headed down. And we jumped into the space shuttle program. And I have to say, after that first few years, nothing that I did in school had anything to do with where my career ended up.
Kind of like how teachers today will tell you that you'll use algebra all the time and you won't.
And I will say,
for most people, you use the shit out of algebra. Yeah, but for most of us,
I use a lot. I use more trig than anything else, because when you're doing drawing, review, and verification, you're always going, okay, what's that angle and what's that length and what's that thing, what's that one, just to get to, is that dimension correct on a drawing?
So if you paid for an education you used very little of later, was it just simply because the program was so unique and new and it was just never been done before?
It's like any education. You study everything, and then usually you focus on a small piece.
Okay, I could see
and
that.
Again, I never used any of my aircraft design aspect of my career.
Yeah.
I did. It was actually an astronautical degree, so I did do a lot of orbit dynamics. I was never a big thermal guy. I was never a big electrical guy.
Okay.
But as time grew, you got smarter because you knew how to learn.
Yeah, you had that foundation.
Yeah.
And the learning process itself.
Yeah, the learning process is the same. It just depends on what small aspect you're trying to focus on. But
damn. So go ahead.
No, that's right. I a lot of my friends have always told me, you have a cool job.
Yes.
Right. And I'm going, the fun part of the job was being able to work small projects, beginning to end.
Yeah.
Conceptual to actual creating a reality, building it, testing it. And then if there was a man in the loop, which most of my projects were, then you actually have that man test it to make sure that he can do exactly what you're asking him to do.
Damn.
And you got to start from a blank piece of paper, and then you get to a final project where you have hardware and you have the guy who's actually going to use the hardware train with you, test with you, and then actually execute it on orbit.
But that same model applies to a lot of things, like designing a new action figure, for instance, and it's still not as cool of a job. You definitely have a cool, that still is applying that same model.
And a piece we really haven't talked about, but when they actually execute the spacewalk on orbit, I'm in one of the back rooms at Mission Control, walking that guy through the process, through the procedure, through the headset on. And again, I always called it the way back room because, there's the NASA front room, then NASA has all its back rooms, and we're the engineering core, a couple rooms behind that.
Yeah, it's dimly lit. They don't even give you good coffee.
They don't. And then, but what we do is, when you get the call back there, that's because they need to know.
Right.
It's
like, oh, now you need me.
Well, that's okay. That's
all
okay.
right. Yeah.
We know our place, and when you have a problem, that's where you go back to.
So what was an example? Because I want to ask you one more question about the vomit comment, but now that we're on this thread, and I want to be on this thread, what was one example of an issue that you were able to, over the comms, walk an astronaut through, spacewalk an astronaut through?
There's innumerous. He's walking through a procedure, right? And every step along the way, you've tried to train him about how that mechanism worked. I mean, a real good example. There's a fluid systems for the cooling outside on space station, and there's lots of quick couplings for all these things. Well, there's obviously a cap that goes over the male, and you bring up a female on a hose, and you undo the cap, and you plug in this connector, and you actuate a bale, and then you've got a good fluid path.
Okay.
I remember an astronaut in particular went up to one of these capped interfaces, and we told him how to remove the cap 100 times. He got up there to do the first one, and he's going, "It's stuck." And we're going, "Do you remember I told you way back when that you need to pull to unlock a latch, to disengage a locking mechanism, and then turn?"
Yeah.
So you need to pull and turn, as opposed to just try and unscrew it.
Like the opposite of a childproof prescription bottle.
Same idea.
Okay.
Right? And he even said on orbit, "I know Curt told me that, and I lost that bit." You know.
Well, and think about it too. I mean, you're up there. You've got to you can train and train and train down here, which is why you want to do an abundance of training. But once you get up there, psychologically, it's totally different, man. You're outside the ISS. You're floating around this marble in space that we all inhabit, and you can psychologically kind of,
I'm kind of afraid of heights. When you get up to a really high spot and your knees start doing that heebie-jeeb,
God, yeah.
Can you imagine stepping outside of a vehicle and not even having a floor?
Yeah.
You don't even know how high you are. You're just out there, 200 miles in space.
Right, and especially if it's your first spacewalk to do, and you've got to go out there and achieve a directive that you train for. And I like, though, that he couldn't remember how to do it, but he remembered that you were the one who told him, "Don't forget this."
Yes. Yeah. And he said, and when he after we got, and again, in mission control, an astronaut on the ground is the only one who talks to the astronauts on orbit. But that astronaut on the ground is talking to all of us in the back rooms.
It's like a game of telephone, but it's got to be way more accurate.
It's kind of like this. Everybody's wearing headsets, and it's controlled conversation, but everybody has a chance to communicate. And but it got back up, and as soon as we told him, to disengage that, you need to pull and then turn, and he's going, I remember Curt told me that, I forgot.
Your voice is on a NASA transcript somewhere of him saying, "I remember Curt," or his voice saying your name.
Yes.
That's so great.
He's recorded.
Yes.
He's recorded saying
yes.
it. But it's too much fun. I mean, but that happens quite a lot because things don't always go smoothly.
Of course.
And then if something doesn't work, I mean, we talked about earlier, things freezing up in cold and loosening up in the heat. So, I mean, a communication would be, we tested that, it got better when it got warm. So then you communicate up to him, wait till the next sun pass, let the thing warm up, and then actuate it again.
Were there things that you guys tested on Earth that you knew would do better if it was warmer, that you waited for the sun cycle to go around for that EVA to occur at a specific heat, a specific thermal range?
There are some things that you don't have a lot of choice, but you try and design it for the whole spectrum so that you don't have to do that.
Of course.
A spacewalk is only 6 hours. So you go through 4, I think I mentioned, orbits, 90 minutes. So you get 30 minutes of a night pass, an hour of a day pass. And you don't want to limit what you can be accomplishing in that 6-hour interval to waiting on the proper environment to come around.
Let me ask you this, and this is going to sound stupid, but I just thought about it. So why not just orbit where you're always in the sun? Why not do like a semi-polar orbit or something like that, or a polar orbit to where you always have sun facing you? Because they're always at equatorial orbits, right? They don't really do much polar orbiting?
You don't, and the inclination of the station, I should know this, it's 52 degrees, right?
Well, I'm going to go with yes.
Degrees.
You're the
Doesn't matter.
You're the expert, yeah.
You're at an inclination, and you're just, that inclination defines what you're doing.
Gotcha.
In order to do that, you need to be going, at north-south the whole time and always facing the sun. And you really don't want that, because then one side of your vehicle's always cold and the other side's always hot.
Gotcha, like a phase-locked planet or something like that.
So you want to be in a rotisserie mode.
Okay, that makes sense.
To where it's always different.
I never thought about it before. It was just something I was wondering, if you have to time those things out, but the ebb and flow of it that's the tolerances you guys planned for. And so of course that's what you would want. want to have.
We were starting on test facilities, but before I get off that,
Yeah.
it was another big aspect of any astronaut training is doing underwater work at the Neutral Buoyancy Lab.
Yes.
And an astronaut, for every hour he spends on orbit in a spacesuit, he tries to get 10 hours of underwater training for that hour of work on orbit. So their rigor is, getting 7 to 10 times as much underwater work doing what you're going to ask them to do on orbit.
Makes sense.
And that gives them muscle memory, right? Practices, works out techniques.
And confidence is just a series of successes. So you want that.
And the Neutral Buoyancy Lab at NASA, it's, the best pool in the world. It's 100 feet by 200 feet by 40 foot deep. And in that pool, we put basically the entire space station.
Ooh.
So there is and it's for external work only. So we have modules, but they are just, cans.
External.
Right.
Because you wouldn't need to simulate that in the internal.
Correct. You're not going for internal. You're already worried about what's on the outside.
Right.
But the whole thing is out there. So we can put an astronaut in a spacesuit. If we need him to translate from the airlock to wherever he's going to do his work, he can plan his route. We design space stations so we have a special handhold everywhere he needs to go. We call them translation paths. So he's figuring out how to get from point A to point B to do the job you're asking him to do. Yeah. Once he gets to the work site, you have him set up his work platform. He's bringing all the tools with him. He brings a foot restraint to set it up next to where he wants to be. And then once he gets there, he's doing the job you're asking him to do. Change out a piece of equipment, assemble a piece of equipment. And I mean, the cool part about the job was always, before we actually got to doing it on orbit, we did it, in test environments. We did it in simulators that were similar in design enough to prove the mechanical. And then when we got further along, we tested it again, the actual flight hardware, before it went into the shuttle payload bay. And then after it gets out and it gets executed on orbit, you get to see that end of it as well, where the astronaut actually touches the actual mechanism and it actually functions on orbit.
Damn.
There were lots of problems that you have to solve real time, and that's why they want all the engineers in mission control. If I need a real time fix, I need a quick answer.
Right.
So I want all the smartest people that were involved in that aspect of the project with a headset on, so that we can ask them any question that might get us to a quick solution.
And so I guess the Neutral Buoyancy Lab, that pool is the most cost-effective way to do the closest simulation of zero gravity that you can.
Underwater neutral buoyancy, like scuba diving, is the best zero gravity environment that we have on Earth.
Besides zero gravity. Why not just make it like a gigantic zero gravity chamber? And aren't there vacuum chambers that you can do to simulate that?
Not zero gravity.
Okay.
Right? There's vacuum chambers to create a vacuum.
Right.
But they're still in 1G.
Okay. See, this is what I was wondering, because they do this test where they drop a bowling ball and a feather in a vacuum, and so they land at the same time to test that Newtonian theory, right?
Right.
Okay. So, but it's still affected by gravity.
It's still affected by gravity.
Okay.
So the only way, we mentioned the Comet, the zero gravity aircraft, where you're basically skydiving, right? And you are in zero gravity when you are free falling,
right?
Okay. And then the most controlled way to do the environment is underwater neutral buoyancy.
Right.
When you scuba dive, you put lead weights on you to compensate for the air in your tanks, and you get to a point where you're properly neutral buoyancy is when you're not going up or you're not going down.
Right.
And we do the same thing underwater. We put the astronaut in a spacesuit is basically a balloon underwater. So we load him up with lead on his ankles, on his back, on his chest to give him a proper orientation you want him relative to what he's doing. But then he just manipulates his body without, kicking like you're in water, or, just using hand over hand translations to get around.
And does it still balance out if they need to go do something upside down? They're able to kind of 360, or they kind of have to be oriented a certain way because of the way the weights are arranged?
You can go inverted in the spacesuit.
And it's basically the same thing?
It's harder on a person because all the blood rushes to your head.
Yes.
So there's protocols that says you can only do that for a short amount of time.
Okay.
And then if you stay in that inverted position too long, they right you for a minute, let you clear your head, and then put you back into it.
Because in zero gravity, it wouldn't matter. That blood's not circulating in that way.
Correct. It's not doing it. But on the ground test, you try and set up the test environment so he's heads up in the pool.
Okay.
But that is the best way to simulate zero gravity is underwater in a pool. And NASA religiously trains all spacewalk and astronauts to in the pool to the best simulation of anything they're trying to do on orbit.
Did they ever let you put on a suit and go down there?
I want to say I have about 70 hours in a spacesuit.
Damn.
Testing out hardware that we actually built and assembled underwater.
Yeah, because you'd need to get in there to know how the scissors work that you designed the handles for.
And really, they typically run what we call an engineering run before we run a suited astronaut run.
Because you can work out all the kinks for the training.
Correct. You don't want to waste their time doing, working out things that were not properly done in the test setup. So you want to make sure everything's set up correctly to run it through it. And early in the program, engineers were getting in suits often to do that first test run. That first, you're just doing the first cut at the simulation.
Yeah, because you're basically writing the training manual for it.
Correct.
In that run.
And you're also, you're fleshing out the procedures you've developed that you're going to work with the crew member. So you're not only testing out the hardware, you're also testing out the choreography of the test.
Right.
And that's all part of the job.
Yeah.
And it just depends on what aspect. We had people that they were dedicated to running the tests and writing the procedures. And there's another set of people that were dedicated to getting all the hardware ready and configured in the pools ready for the test.
So it's based on the way the hardware is designed is how the procedure's written for the repair, not the other way around. They don't write the damn procedure and then design it a certain way.
No, it's always...
One doesn't affect the other. The design's there.
Procedures always last.
Right,
and you just got to make sure that everything's built to the requirements so that you can write the procedures. And it's going to work with the astronaut. It's going to work with the tools. A simple example is your choice of tools on orbit are a 7/16 bolt head or a 5/8 bolt head.
Okay, that was something I was going to ask.
So, they have a cadre of sockets and tools and extensions that are set up for 7/16 and 5/8. So if you have a high torque application, you're using a 5/8 bolt head and a larger tool. If you're using a smaller bolt application, you're using something like a Makita and you're putting a socket on the end of it.
Okay.
But again, that bolt head has to be designed specifically to work with the tools, taking into account all the thermal extremes.
Yeah.
Because even metal shrinks and grows. So you got to just work all that out as part of your design. And then when you get to the point where you're actually building the procedures and testing it, it should work.
So do they have both on your automatic tools, like you said, like a Makita? Like, do they have battery powered and pneumatic, or are they one or the other?
Pure battery.
Pure battery. Okay, so no pneumatic tools whatsoever. Okay.
Nothing.
So you need a real high torque if you need it built into that thing.
And you want to talk about an expensive tool.
Oh,
there is it actually has an onboard computer on it too, so that it can record all the data. And again, it's like running torque, final setting torque, and it has a little display that the crew member can read. So if I tell him to torque something up to 10 foot-pounds, the tool, he sets it to that setting, he drives it, and then the tool tells him the set torque that it actually accomplished.
So it's good. They're like, you're good. Stop there.
Yeah, it stops itself, and then he just confirms that he got the torque that you wanted.
Visually on the screen.
And it's got, level 1, A through F, level 2, A through F. So you have like a dozen settings to work from, and the first one's 2 foot-pounds and the last one's 25 foot-pounds, and every couple of foot-pounds in between.
Is that something they have to remember? Will you say, go into this tool, set it for this foot-pound, go to 3F, and then they'll just set it to that and then stop at a certain point?
Well, and it'll like a Makita, it's when it gets to that proper speed or that proper torque, it stops itself.
Interesting.
Or in the case of an on-ground tool, you get that ratcheting sound when you hit the torque you want. In this case, the tool stops when it realizes the torque that you go to. And again, you tell the astronaut, go to setting A3.
Yeah.
He goes to that setting and he said, okay, go to that. We need about 10 turns out of this. And you should torque out when you're done.
Wow.
He sits there and it tells him how many turns he went, and it tells him what torque it's set in. And he reads that back to us on the ground so that we can confirm he got the right direction, he got the right number of turns, and he got the proper torque.
And it's just a teamwork, not only in design and implementation, but even things like that, just simple operations is fascinating, because you don't want that guy having to think, or that guy or girl having to remember all those conversion charts. They got enough things to think about. They'll relay it to you. You guys can confirm and then relay it back. The teamwork element of this is something that's so impressive. How many people it takes.
And if he's working a power tool, you know, you send up to him. I want it to go clockwise. I want it to be this torque setting, and it's going to be about this many turns. So he understands how many turns, and he can watch the tool turn.
Yeah.
It's usually not high speed, so you could watch it turn, or you could just watch the counter on the tool. But typically, if you say go to hard stop, he just goes until you hit that hard stop, and then he verifies with the tool that it reached the proper torque and turns. They relay that to the ground so that all of our structural guys that are sitting in those way back rooms can go, okay, that bolt was properly engaged, torque and turns as we expected, and now you can move on to the next bolt.
Damn.
And I mean, you're going through step by step by step for every turn of a wrench.
Yeah.
And it goes on and on. A lot of the aspects of the equipment we use, I mentioned medical field has a lot of tools that we have stole from. Sailing is another area where you use a lot of tools.
Sailing.
Pit pins in sailing, that's usually a pin that you put a clevis lug situation, and you put a pin in there that has a little ball detent on it that keeps that clevis and lug in place.
Kind of like a cotter pin?
Or a quick release pin.
Oh, okay. I see what you're saying.
It's not really a cotter pin, but it's spring-loaded quick release pins.
Yes.
We use that design on Space Station everywhere. So if you can get away with a pit pin application, if it just needs to be secure but not really tight,
right,
you put a pit pin in it, and a crew member can actuate a pit pin with fingers.
Yeah.
And if you need that kind of an interface, we use it everywhere. Another big one was a French hook. That's the quick hooks that they have in sailing. It just has a little spring-loaded little clasp, and it's a stainless steel hook.
And that's what they hook themselves onto so they don't go flying off. That's their tether apparatus, right?
Or anything that you can hook by that kind of a hook. We can buy that stainless steel sailing hook off the shelf and pretty much use it.
Damn.
Okay. With minimal testing to make sure there's no lubricants or goos in there. That was another thing we talked about, weird thermal extremes.
Yes.
If you introduce grease, which we do on the ground on everything, you introduce a little bit of lubricant to make things work a little bit better.
Yeah.
That doesn't work in space.
Well, but we only need to do that here because of friction, right?
Yeah, but mechanisms have friction in them already, right? So it's reduced in space, but if you have introduced a grease into a piece of hardware before it flew and then you fly it, that grease will freeze up.
Oh.
And so
then it does the opposite.
It does the complete opposite of what you're asking it to do. So typically you got to get everything designed in it. You don't use lubricants. You don't use anything. It's got to be spring forces, positive latches, positive detents that are don't involve anything like what you would normally do on the ground, which is, throw a little WD-40 on it and it'll work fine.
Yeah, garage doors sticking up on you.
Yeah.
But you've got to do all that within the tolerances also of the heat extremes, so the ebb and flow of the actuation of the actual material. And then you've got to do this within tolerances of not needing a lubricant to do something that you would need a lubricant to do.
And they make dry film lubricants.
Okay.
And those are I can't remember, graphite lubricants that you see that in a lot of applications. And they do have some of that on orbit, which is, and the problem is usually has to be minimal because anything that's a spray-on dry application will probably flake off.
Oh, okay. That makes sense.
Whenever you're dealing with astronauts in a spacesuit, the biggest priority is always safety.
Of course.
So you don't want him to hurt him or herself.
Yeah.
You don't want whatever you've built to break, fracture, crack, and create an unsafe environment.
Yeah.
If you're using a braided wire, you don't want it to, break one of the braid strands, and then that turns into a needle.
Yes. Flying around the Earth at 18,000 miles an hour.
And an astronaut just so happened to translate by it, and he caught his glove on it, and now he has a leak, and now we're going back inside. So everything is driven by safety of the person, safety of the hardware you're providing, so that you're not putting that crew member in an unsafe configuration.
Damn. And that was mainly your job, was to make sure EVAs were functioning properly as far as those implementations. You didn't do a lot to do with the internals.
Me personally, no.
Yeah.
But there's a whole nother team that deals
cool.
with internal. And one of the things I was trying to say, astronauts, my job was to train them for a spacewalk. So if they had in the shuttle days, they had a 10-day mission, and they got to do 1 6-hour spacewalk, I go on a 10-to-1 training program with them to make them good for that 6-hour period.
So you stick with that one astronaut,
or pair or whatever, or
because you have one in a backup, right?
They always go out 2 at a time.
Okay.
Right, but both guys need to be trained on what they're doing.
Yes.
And that is 6 hours of their life while they're on orbit for, let's say, 10 days.
Yeah.
You can imagine all the other training they were doing for all the other things that they have to do in that time. And to be able to grab that person and get him to focus for the time that you have with him, and then actually have him remember.
Yeah.
It's a very tough job for them.
Yeah.
And my job was to make it as easy on them as possible for that 6-hour time I need them to pay attention when they're doing a spacewalk.
What's an astronaut's sense of humor like? Who was your favorite astronaut to work with?
Joe Tanner was one of my favorite astronauts. He flew most of the Hubble missions.
Oh, okay.
And then moved into space station after we got away from the Hubble programs, and military pilot all his life.
Yeah.
Worked in the industry. I couldn't tell you how many years he was an astronaut, but it was a lot.
Yeah.
And trained him on STS-4.
Oh, okay. So your first stand mission.
I'm sorry. I misspoke. Not STS-4,
okay.
but the fourth space station mission.
Oh, okay. Yeah.
Which was actually like STS-97.
Yeah, because it was after Hubble. Hubble was 31, right?
Right.
The launch of. Okay.
There were several launches for Hubble, but yes.
Yeah. Okay.
Repair missions for Hubble.
Oh, okay.
I mean, I think they had 6 or 7 over the life of the shuttle. But
wow.
on the fourth space station mission,
okay.
I trained him, and then I trained him again on the 12th space station mission. So he was known as the guy who was very familiar with the electrical power system.
Oh, okay.
We put up 4 separate payloads as the different generators on space station. There's
Right.
4 separate large elements. So he was like the most proficient astronaut at that hardware.
Very cool. Was that something he technically had a knowledge of, or he just worked really hard at it and got to know it really well?
It just he got to do the first one, so every chance they had for him to do it again.
Oh, so he got practice by force. Yeah.
So the first one was in 2000, right at the end of 2000, and then we had the Columbia accident.
Right.
So the next one actually got pushed out several years past that.
Right.
And then so he probably hung around for 6 years waiting for that next one to come up.
Yeah.
And it happens a lot, but I mean, he loved it. He wouldn't trade it for the world.
What made him your favorite? What's your favorite story about him?
Just in general, very hands-on. I told you before the podcast, I have an old 280Z that is my
beautiful
toy.
car.
He has an old 240Z.
Oh, okay.
And he worked on it all his life to keep it on the road. So we got a real camaraderie with our cars. And then that just rolled into training. And he was military, like I mentioned, military pilot. Mm-hmm. And the military pilots were always the easiest to train to do spacewalks because they were all hands-on kind of guys.
And already had the balls for it. They weren't mentally distracted by that.
They chose to do this.
Yeah.
Come on. That's their feather in the cap is to come out of the military and actually get into the astronaut program.
Absolutely.
So they were in hog heaven and throw any problem at them and go, we'll fix this.
Yeah.
And it just seemed the military guys were always the most can do. And I don't mean to downplay all the rest of them, right? But they were always the easiest to train, the most common sense knowledge, the most hands-on experience.
Yeah.
And the hardest ones I usually had to train were the doctors, the PhDs.
They weren't distracted by the danger like the military guys trained were.
And I don't really think there's a fear factor in it. It's just they don't have that same kind of hands-on experience.
Yeah, they use different sides of their brain.
They're in a little less familiar territory.
Sure,
I mean, we're teaching PhDs to turn wrenches.
Right.
If you got any wrench turning experience in your regular life, it's simple. If you don't, it's much harder.
Yeah.
Anybody these days, nobody wants to work on their car because they just don't understand them anymore.
Right.
Right. In my day, everybody had a tool bag and you fixed your own problems.
Right.
And life is just changing. Mm-hmm. And doctors don't have to turn wrenches. Yeah.
Well,
right?
I mean, look at and I want to talk about SpaceX a little bit here in a little bit, but look at the new SpaceX, the Dragon capsule that just went up. It's it's flat screens and buttons. There's no knobs. There's nothing to turn. There's barely anything analog about it. And so it is a different mindset, right?
You should see the shuttle. It's the old, finger protected switches. You know, they got a little guard on each side that can only go one way up or down. And there's 1,000 of them.
In the space shuttle program, the STS
space
programs,
shuttle
not the
program.
Dragon, the SpaceX
Not the Dragon,
stuff.
not the newer
everything's
stuff.
very
Everything
analog.
is-
And these guys are just sitting there, and then they just kind of touch a screen.
Everything's like a Tesla. That's right.
That's right.
No knobs in a Tesla.
Because it's all automated. I mean, they really do. I don't know what they do in that.
Computer touchscreens. That's all it is, and that triggers whatever you used to need a manual switch for.
Yeah,
it's great. That's technology.
It
as
is
we know
technology. It's interesting. I don't know how much I don't know how much benefit that is to change, other than it takes the responsibility out of the pilot's hands, and it's basically just an automated type of a deal.
And it doesn't take anything out of their hands. It's just a different way to trigger it.
Mm-hmm.
You know, they still have to be there to initiate the commands. Right? They're just not throwing switches anymore. They're doing a touchscreen.
Yeah.
And that's good that technology's moving that way. It's much lighter.
Mm-hmm.
It's much more efficient. A lot less likely to problems. Except it comes. I mean, how often do you have a problem with your computer screen?
Oh, never. This thing works perfectly every time. No,
yeah,
all
right.
the time.
I know. And so I mean,
all the time.
It has its own failure modes, but.
So I also want to just, before we leave the test facilities part of it, your first time in the Vomit Comet, what was your experience? How did you feel about it? Just your first time.
No, that's all right. And the first time I did it, we were working on a simple mechanical bolted interface, and it turned out that it was a bolt on a cable. So as you torque the bolt, you got tension in the cable. And that was just like a clamping device, right? Like a turnbuckle kind of a configuration.
Mm-hmm.
And it turned out that when we took that to thermal extremes, it took a lot more torque to undo it than we set it to. So if you set it to, let's just say 25 foot-pounds, if I take that into a cold thermal environment, it took like 50 foot-pounds to release the torque. Because as things got cold, they shrunk.
Right.
And you created higher compression, which means I had a higher torque to release it. Simple.
Yeah.
Our requirements say a crew member can only put in 25 foot-pounds into an equation to engage or break a torque. So I had test data that said I needed him to break 50 foot-pounds. And so what we did is we simulated that in a test stand in the Vomit Comet, went up on orbit, and we said, okay, I'm going to set that to 50 foot-pounds. Show me that when you're free floating in a simulated zero gravity environment, can you release 50 foot-pounds of torque with this torque wrench that I just handed you?
Yeah.
It's not a simple thing to do because you can't react.
There's nothing to push off.
There's no
torque of your own.
You grab a handle, and then you're pushing with the other one, so you got to react it all through your arms and through your chest.
Right.
And that's why they said 25 foot-pounds, because they don't want you to overexert yourself in this uncomfortable environment. And we proved that the crew member could apply 50 foot-pounds in this configuration with this handhold relative to where that bolt is and how he would need to position his body to break the torque.
He did it no problem. He was like, yeah, I got that.
And we knew it was not going to be a problem, but we had to prove, I mean, the requirement is less than the true capability of a person.
Okay, that makes sense.
They're trying to stay a little conservative.
Sure.
Right? But we knew he was going to be able to do it, but we had to prove it.
Right.
So we set up this test configuration. We flew it 20 times. We put 6 astronauts through it, so we did it a bunch of times.
Yeah.
Because your capability is dependent on the person. So you put, smaller people, larger people, and you just let them keep trying it until you prove it. I collected the data, and I went back to the owner of the requirement and said, they can handle this. Here's my proof. And then they said, okay. But that was my first experience, and this was probably in the late 90s.
Experimentally, that was cool. What about experientially? How did you like being in a simulated zero gravity environment? What did you think? I knew you were focused on job, but did you get a little chance to enjoy it?
We get to play a lot. And there was one case I mentioned to you when we were doing the goo experiments.
Yeah.
And they had this really technical apparatus that was holding the goo and holding the catalyst, and it was a pressurized system that was releasing it through, a tube that was a specifically designed, hose and nozzle system. and that the pressurized chamber that they were holding all this in blew a gasket within the first couple runs. And it was like, okay, well, we're done.
We got 18 more of these to go.
Well, there's 3 other payloads that are doing other experiments while we're up there. So
okay. So your job was over.
my job was over. So we just got to ride for the next, 20, 30 parabolas, and we were able to play.
Damn, that's cool.
Yeah. And so
Did you bring little balls and stuff up there to play, or you just float? I mean, just enjoy the zero gravity, just spin around?
You do, they called it the hamster. Yeah.
Oh,
you
okay.
run up and down around the internal volume and just kind of just run around. Somebody grabs you and they just spin you.
Yeah.
So you're sitting there and you just spin around yourself, or you could always throw things back at one another. We always had, pens or Sharpies or whatever. You just throw them back at one another and see how they handle it. But yeah, it was always fun. And I got to say, it physically never really bothered me. Mm-hmm. A lot of people, you just can't handle the roller coaster ride, and they get nauseous. And that's why you get the Comet. They get nauseous, and the worst thing you can do when you're running a test like that
is vomit.
Because I don't know about you, but when I smell something like that, that makes me want to vomit.
It's a chain reaction. Yeah.
You don't want to get that everywhere and then get everybody feeling nauseous.
Did that ever happen? You went on a ton of these things.
Oh yeah, it happens all the time.
Yeah,
and you get trained to deal with yourself.
Okay.
Here's your bag.
Yeah.
Don't make a mess.
Yeah.
Right. Here's your tie wraps.
Yeah.
Don't make a mess. And then the back of the plane had seats enough for all the test crew. So there were 40 standard seats in the back of the plane. So if you get sick, go strap in.
Yeah. You're done.
Take your bags with you, and that's just it. Once you started, it was almost impossible to stop.
Oh yeah.
It's kind of like getting seasick. It just gets worse. The longer you're out there rolling on the waves, the worse it gets once it started. So, but luckily, I never had that problem. Always enjoyed it. And when we were doing the Challenger experiments, the Columbia Vomit Comet experiments, we were doing 30 parabolas out and 30 parabolas back, which was a day, basically a day of work. And we would do that 5 days a week for 3 weeks.
Wow.
And just keep doing it.
That's your job.
That was the job. And we had a crew of people, we called it the Goo Crew.
Okay.
And we would all get together and we all knew what our objectives were, and we just, bear through it. And every time you got different astronauts, different test criteria, different whatever it was, and you just keep repeating it.
Damn.
But it's fun when it's in a cool test environment.
Absolutely.
When you're just sitting there watching, crystals grow or something, it's not so exciting.
It's a little different.
A little bit different.
So tell me about the solar panels that you helped.
I think I mentioned as part of the job, I work for Rocketdyne, which is a branch of Rockwell International, and they were responsible for building the power system for space station. So it's solar power, batteries, charging like any rechargeable battery system you have here on the ground. The problem was the amount of power you want available. So they wanted over 80 kilowatts continuous power, which is a lot of solar cells. And the blankets for the solar cell, there were 8 sets of blankets, and each one was 30 foot wide by 100 foot long. And to fly that, right, it compressed down to an accordion, a mass that was like Tinker Toy style.
Oh, okay.
That deployed and retracted on its own.
Okay.
And the panels were accordion folded so that they closed down to something very, very small. Mm-hmm. And then when you got up there, you self-deployed, and you have these big sails coming out. 30 foot by 100 is massive, and we had 8 of those. And
you were instrumental in aiding in the design of how those would roll out.
And the design, we had companies that specialize in solar technology.
Okay.
So they bring to the table a concept that will work.
As far as material that will be able to do that, and as far
something that will accordion fold, right. Something that will fit in this compartmentalized small thing. And our job was to, if it needed to be assembled, if it needed to be actuated, we had to prove out that if it was replaceable, You had to retract it, unbolt it, replace it, redeploy it. Anything like that. So everything was made to be modular,
Right.
so that it was replaceable. We call it ORUs, on-orbit replacement units.
Right.
Everything was replaceable. So if and when it failed, it was easily replaceable.
Wow.
And with the solar panels, these things were designed. We launched them. The first one launched in 2000. It was designed with a 10-year life.
Oh.
That was 20 years ago now.
Oh, wow. Okay.
So they're still functioning.
But that's just like Voyager or anything else. They plan for it to break down in a certain amount of time, and it way exceeds that.
It does. I mean, that's a life experiment.
Sure.
But still, we're 20 years in now, and those first solar arrays aren't performing near what they were performing when they were first deployed.
I bet not. Plus, the technology's gotten a lot better since then, right?
Yes, but being on orbit, it gets hit by micrometeors.
Sure.
You get, and it was designed to be about twice as efficient as it needed to be.
Oh, okay.
So that when you get small hits and some strings start failing, you still have enough backup string, or you have enough strings remaining that you're still producing the kind of power you need to produce. 20 years in, they're getting to the point where they're not producing as much power as we wanted.
Yeah.
So they were initially burning out 20 kilowatts. Now they're at 10 or below, and they're just getting to the point where they're not good enough anymore.
Yeah.
So NASA has paid for a new set of solar arrays to be put in place where the old ones were.
Huh.
And now we don't have the shuttle any longer.
Yeah.
Right. So what are you launching them on? So we're driven by the constraints. You mentioned the SpaceX Dragon. That's they have an external cargo bay
Right.
that you can launch things on. So we designed a new set of solar arrays that would fit in the constraints of the Dragon trunk.
Wow.
And again, you take full capabilities of the new technologies.
Sure.
Solar arrays, they're now, instead of being a hard substructure, they build them on a flexible substructure. So the new designs for solar arrays are more like paper towel. They roll up in a circle as opposed to accordion folding flat.
Right.
And then when you deploy them, it's a much easier mechanism to
Because it
deploy
just
them
pulls
because it just
along a track and
it
unrolls like you're pulling a
it-
paper towel or
It just
toilet paper.
unrolls. And again, the solar cell technology has gotten much better. It's much more efficient, less surface area required. So we helped design a whole new set of new solar arrays. And my job was, again, the mechanical side. Here's how we're going to fly it. Here's how you unbolt its launch restraints. Here's how we transport it by a human being out to where it needs to be. Here's how you tap into the existing system. Here's how you structurally mount it to the existing thing that's already out there. And then you deploy this new array over the old array. And the new array is smaller, shorter, shadows the one behind it, but that one by itself is enough to meet your power needs.
So you use the existing structure of the array that's already there, but that's damaged that you need a new solar panel on. So you don't even take the structure out, you just put a new one over the top of it?
Yeah, you're
Why would-
basically...
Yeah, because it's more efficient.
Well, and again...
You don't have a bunch of space debris. You don't have to undo it, jettison it off.
We could have done that.
Yeah.
But then we didn't want to create the problems that goes along with. Then I need to have a dedicated spacewalk to go out and jettison it.
Right, and that's true too.
And I don't want to spend that time if I don't have to. So they left everything in place and they just built over it.
It's a much more efficient way to do it. It's smart.
Right. And then all of the solar arrays, they're built on roll rings so that you can always point them to the sun.
Right.
So that whole mechanism you don't need to redesign.
Yeah.
Right. So all I'm doing is creating a new sheet of solar cells and taking advantage of the existing design of the mechanics behind tracking the sun with solar panels.
Damn, that's cool.
And
Patrick, do you know that?
I did not know. I knew they were flexible, but I didn't know that, how much thought went into utilizing what's already there.
Yeah.
In other words.
that was, again, you want to take advantage of as much as you can that's up there. You don't want to reinvent the wheel.
Yeah.
And so
Just make it roll smoother.
and the bearings associated with those roll rings are very complicated. And they not only can spin freewheel forever, they pass electricity while they do that. Very cool mechanism.
Very cool.
But again, get outside of the mechanism, I'm not supposed to care. I'm just asked to assemble it
Right.
and build it and strap onto it. So My job was to make the mechanisms so that they could bolt onto it, actuate it, get to it, and then, push the buttons to deploy it.
So the solar panels on either side too, right? So did you have to do this twice?
There's
is it just
typically
one?
a solar panel is one side.
One side, okay.
So you always rotate that panel to face the sun, and it's always the same face.
Okay, I don't know why I thought there was two,
That's
or
okay.
one on one side, one on the other, or
And
that it worked from both directions. I knew they rotated.
They rotate,
Yeah.
so typically you only
So you don't
have
need
one functioning side,
Makes
and
sense.
the other side is always in the shadows.
Makes sense. Damn, that's cool, man.
Yeah, and again, you learn a lot about solar technology,
Mm-hmm.
and I mean the only reason that solar technology is so available
Mm-hmm.
anymore is from what we learned putting things in space.
So dispel the myth that SpaceX doesn't need NASA.
Easy to say, but
Mm-hmm.
NASA pays for everything.
Yeah.
So it's easy to say you don't need them, but
Right.
until you can find somebody who wants to fly all the time,
Right.
and it's not a lot of the design, a lot of the money that went into the design for the SpaceX Dragon and all of his cool technology came from NASA seed money. So if you didn't have that seed money to actually do the design and development and the testing and then the actual execution,
Yeah.
and Elon Musk is incredible.
Yeah.
Right. I mean, he is so smart, and he has such ambitions for people and technologies that, I mean, he's pushing the envelope in every aspect.
Sure.
He is a competitor for Boeing, so I can't say that I like him,
Right.
but he's awesome.
You have
right?
to say it, yeah.
Yeah, and but everything he's done, when he first landed those the first stages back on the
Yeah.
ground, I never thought that was even possible.
Yeah.
In an interview that he made before the first one, he said, I give it about a 50-50 chance of working.
Damn.
And I sat there and I said, okay, I've worked in the space industry all my life.
Yeah.
99.6 was about the furthest I could ever go down on probability of success. And
Right.
he's going 50-50 shot. I'm good.
But
you
it's
know?
his, like you said, it's his money, but it's NASA's seed money that's doing that too. Because
But-
there's a big disconnect between what they think NASA's role in SpaceX is, and they're actually they're bedfellows.
I think, oh yes, completely. Right. But what it's done is it allowed him to bring in the technologies that allow him to push the envelope.
Yes. Yeah.
Right. And landing first stage is almost commonplace anymore.
Right.
Right. He flew one of his heavy lift vehicles, and it came down too fast and it blew up on the thing. But he says, I got about 80% of the data I needed, even though we had a catastrophic explosion,
And they'll do it. They'll figure it out, and they will.
And
'Cause
he
it was pretty damn close. It just landed a little hard, right?
And yeah, it came down.
a little hard.
Something didn't work properly,
Yeah.
and he came down too hard.
Yeah.
And but again, that's the problem with most of these. It comes down at a little bit of a wrong angle, or it comes down not where it was supposed to, and it lands on something it wasn't supposed to, or he's hitting the barge and he misses the barge.
Right.
But to be able to actually have the ability to execute that,
Yeah.
it's awesome.
It changes the game.
It does.
Yeah.
But he's just getting into human space flight.
Mm-hmm.
And I don't mean to be a naysayer, but when the accidents happened on the shuttle, the programs were shut down for 2 to 3 years.
Right.
Until you dug into every aspect you could of what the problem was and how to fix the problem. But while you're down for that period of time, they go back through everything. It's not just the one problem that you got into. They want you to review everything to make sure there's no other misses like that along the way.
Exactly.
And it takes a long period of time. So if we have another accident, it's going to be very hard for even a SpaceX to recover from that. He recovers from accidents pretty quickly right now because there's not a man in the loop.
Right.
But if we ever have an accident where there's a man in the loop, it's going to be the same kind of protocol that you step back, you research everything, and you figure it out.
Yeah, because the Challenger one, the first explosion that happened in '86, that one was due to that O-ring issue that you and I had talked about. But it was the 2 O-ring system. The first one failed every now and then didn't make it past the second one, and still successfully flew. And so they figured, well, there's a bit of a tolerance there, but it was unseasonably cold that day. It was like, January 28th? So it was still cold. It was winter, even though it was Florida.
Still winter.
And it was below freezing for sure, so that froze up. But it was 2 years, and then it ended up adding a third O-ring to that, correct?
And that's correct.
Boosters, okay.
And it's kind of a safety procedure. If you're dealing with any system you need to work, it's usually singly redundant. So like you said, the 2 rings, one can fail, the second one still functions. Whenever you put a man in a loop, you typically go to double redundancy. So now I got to put 3 seals in place from the example we were just saying. So the first 2 can fail, but the third one will still work on its own.
Right.
And you start building systems, all systems, to be doubly redundant. So you put in 4 sensors if you need 2.
Right.
So 2 can fail, so you still have 2 good ones.
Which adds weight.
Well, but and complexity.
Right.
And now software to handle inputs from 4 instead of 2.
Right.
I mean, it just, everything gets complicated the more redundant you get.
There's just so much to it, and this is why I thank you so much for talking with us, is because there's so much to this stuff that I find so fascinating. I know the listeners do as well, that you don't even think about. You know, it's these kind of detailed operations that are fascinating.
And again, from a build it perspective, you have to build it to be redundant, and then you have to prove it's redundant. And then after you get 2 failures, you still have to prove that your function, whatever your function is, actually works even after those failures.
There's a lot of levels instead of back to the drawing board. There's a lot of levels in between that.
Right. And we were talking about power system.
Yeah.
I think I mentioned earlier, there's batteries on space station. So there's 48 batteries. They all weigh about 400 pounds each. And they're about the size, each of them is about the size of a small refrigerator. And I mean, just think about the logistics associated with changing those out.
Yeah.
When we first flew the space station, the batteries on space station were nickel cadmium, NiCad batteries. And we haven't used NiCad technology in ages.
Yeah.
Right? And I actually said they're wrong. They were nickel hydrogen, which was the predecessor to nickel cadmium.
Oh.
So they were really
Even older.
old technology cells. And again, we just replaced all those batteries because they also had a 10-year life.
Right.
So then we had to change out and do the math. It was 400 times 48.
Yeah.
You do them a 6-pack at a time.
Damn.
And we're flying up these huge refrigerators, and then we're having astronauts go out there and physically change them all out and then bring the dead ones home.
Oh, wow.
It's a huge endeavor to go that. But now we have lithium-ion batteries on space station, twice as efficient. We had to use the same footprint, but we use half as many, and it works.
So
and you know, you advance your technology. The mechanical interface is the same, but the chemical technology in the batteries changed. So, like you were just mentioning with the solar cells, we got better, more efficient solar cells. We have better, more efficient batteries, which keep the space station moving on beyond its life. Its design life.
Yeah, it's expected.
Well,
Damn, that's cool.
At least they didn't weigh 400 pounds up there.
That's true. That's true.
Gotta be
And,
nice.
Yeah, because you get one
And-
astronaut
You just have one
in
person
theory
doing it,
moving,
yeah.
right? Yeah.
and we did. I mean, we tested all that out. I mean, you do that underwater. You also make the hardware neutral. So they're moving around this, 3 by 3 by 18-inch box that's a battery, and then, they're moving around in the water like it's nothing. You only have to deal with water drag, and if you move slow, that really doesn't come into play. And they just unbolt them, pull them out, hand them off, take a new one, put the new one in, and move on. Sounds so simple, but the actual execution is complicated.
Everything's much harder, though, when you're up there.
It is.
And much more cumbersome, especially with your
and
gloves.
You need to be choreographed so you're not sitting around,
looking around.
twiddling your thumbs.
Enjoying yourself like an asshole. Yeah.
You got to take, advantage of every minute you have, and you don't want a lot of downtime, and you want to be as efficient as you can possibly make it.
Yeah.
Which is part of the training, becoming more efficient, doing it in the most efficient manner as possible, choreographic so it's efficient.
Fascinating.
And it's all good work, good topics, fun to do. And
Fascinating.
I was certified to scuba dive, and scuba diving in the lab. We actually opened up the Neutral Buoyancy facility in '97, and my company was the first one to test the power systems for space station in the pool.
What was that like? You have to go there with electricity.
And again, you're not dealing with electricity.
You're dealing with the components that will operate the electricity.
You're dealing with the mechanical components that house the electricity. So you're not working with electricity underwater. It's just the mechanical volumes.
I would think not. I just wanted to make sure. Okay.
Right.
Yeah.
We're not doing that. But not only were we testing our hardware, we were testing the facility. And of course, a facility like that, first time out the gate, nothing ran smoothly. Right?
It's water. It's a pool, guys. How could you screw this up?
But you need overhead cranes, and we had a shuttle arm simulator. It was hydraulic underwater, So it was working and commandable to work just like the shuttle arm
Cool.
in zero gravity. Again, complicated mechanism. There's a whole division of the neutral buoyancy facility. That's all they did.
Yeah.
Fix the arm, run the arm, drive the arm. And again, complicated mechanism in a complicated environment.
Yeah.
Necessary to do what we wanted to accomplish.
Wow.
But everything was, you run into a problem, you get out of the pool.
Yeah. Let me ask you a question on your. Okay, so did you have anything you wanted to ask? We've just been chit chatting, man.
I do have a question, but it's more theoretical now. So, where do you see the biggest challenge, or how far are we from being able to sustain a long-term lifespan on, say, Mars, an asteroid?
I am, a nice polite way to put this, I am not a big fan of going to Mars, only because if you look at what we got out of going to the moon, it's pretty limited.
Yeah.
We learned that we could do it, but we didn't really gain anything from being on the moon.
We got bragging rights over Russia.
Yeah, and we brought around a few 100 pounds of rocks.
Some street cred is pretty dope, though.
And
international street cred.
We proved the technology. Okay, so that's good. Going to Mars, everybody, is signing up. I want to be the first one to go to Mars.
He signed up.
I did.
And you probably know the physics of it, right?
He's asking for his personal life, and you're
But
just
the-
poo-pooing on it.
No,
You're like, I
I'm
don't
not.
think you should do that.
No, what I'm saying is, the only time you jump from Earth to Mars is once a year when the two planets are as close together as they get in their orbits, right? That jaunt takes 6 to 9 months to get to, depending on exactly how close it is to you when you actually are making that trip. Then a whole year goes by, and the planets are going on their own orbit. And after a whole year, they come back and they get in close proximity again. And then that's your chance to jump off and come home. So let's do the math here. 6 to 9 months to get there, a year, and then 6 to 9 months to get back. So you've committed 2.5 years of your life to do that one time and spend 1 year on Mars. Now, what's the chance that something goes wrong in that 2.5 year period? Like, it's probably 90% that something's going to go wrong.
Of course.
100%.
Right.
Well, 100%
and again, there's and it was the movie Mars, one of the best movies made with technical cred, right? But I mean, they, somehow this vehicle turned around and went back to help him. But if you actually watched it, it was like 500 days later is when they actually got there to help him.
Yeah.
That's like 1.5 years they waited before. So somehow he had to survive for 1.5 years with no help.
Yeah.
The chance of being able to do that is, in my mind, a huge challenge. I'm not saying I'm not saying it's impossible. I'm saying there's just a bunch of prep that has to happen. You're going to be launching modules that land on Mars and just sit there, and that's your resources.
Yeah.
You need water, you need air, you need food, and you got to have enough up there for somebody to survive 1 year and then get back. And then not only that, they have to have a vehicle to take off from Mars and rendezvous back out on the vehicle they're going to come home on, right? Or at least come home. And that thing has to be able to survive 1 year on Mars with no work, no problems. And, and how many times have we aborted a launch because of some small little problem, right? How many times? They don't have a lot of time here. You only get a couple of chances when Mars is passing by Earth to actually be ready to go. If you miss that opportunity, it's another year.
Yeah.
And how much resources do you want to have? Do you want to plan to go do that? I'm not saying it's not possible. I'm saying it takes a lot of resources, a lot of planning. They're going to have to work out some kind of a rescue scheme or system.
I think they were going to send stuff there ahead of time and
That's
drop
the
it
plan.
off. Yeah.
That's the plan.
And so there could be a return rocket, but even that, you miss your window. Now what do you do?
You wait. And then you run tests for another year until that window comes up again. And those are the kind of things that make this a very high risk proposition.
Yeah.
So you think station first, build out further stations so where we can get out of low Earth orbit and then have a resource there.
And I was always a proponent. Let's go back to the moon.
Mm-hmm.
You can prove we can habitate the moon, right? And the real question is, what are you going to learn from Mars? Why did you pick Mars? Right? Why don't we just go back to the moon, learn everything it takes to learn to have to live in that environment, learn how to build modules, learn how to assemble modules, learn how to grow food, learn how to do everything on the moon, so that if we ever had to do it, you got a way to go do it.
Yeah.
And if something goes wrong on the moon, you can get there and save somebody in a I don't want to say short course, but relatively
A lot shorter than Mars.
right, relatively quickly, which makes your emergency backup plans more feasible.
See, the problem here is that that's too practical.
I
and
know.
that makes too much sense. And you don't get the bragging rights to say you're the first person to send something to Mars, because nobody has ever done that in humanity's history.
I agree with you. I mean,
Yeah,
but
that's why. It's not as cool.
When Bush was in office and he said, that was, we were going back to the moon. And I mean, I was going, I am so psyched. That is just going to be awesome, because that's going to be the project that ends my career.
Right.
By the time I get through that, and I couldn't think of a cooler environment, and you're going to start talking buggies and bulldozers and ways and inflatable technologies were coming into being a reality.
Mm-hmm.
We could put inflatable laboratories on the moon. You set up a base on the moon built out of inflatable modules, and how do you secure them, how do you stay down, how do you protect them, all those things came into play, and that was going to be just too much fun, because it was going to be my line of work was having astronauts in the loop doing whatever you're asking them to do.
Yeah.
Building modules, maintaining, whatever it is, and that would have been a great end of career. So now it's back now, and this is 20 years later.
Yeah.
And they're talking about going back to the moon again as the test ground to go to Mars.
That's what they should do.
They should.
Not as dope, let's be honest.
Well, they will.
But it's super cool still.
And that's how you develop the technology to go to Mars.
It makes too much sense. You're an engineer. You don't know what it's like to say that this is cool and that's why we're doing it. You want to go because it's practical, smart, efficient, safe, all those.
But the real kicker is, what's your end goal on Mars?
Yeah.
Why do you want to go?
Sustainable live. And I think that they eventually want to have a second Earth. I mean, that would be for humanity's future. I think they're talking about terraforming the bitch. I mean, I'm still at, you got to have an objective that's achievable. Yeah.
And I don't really think we have an objective. We just want to get there.
That's it. That's it. I was being tongue in cheek when I was saying that your idea was garbage, because it is the smart way to do it. It's garbage in the sense of that it's not as cool. Even though it's super cool, it's the damn moon, right?
Well, not like it's not an accomplishment in the majorness that it is, but the rovers really haven't brought what I had high. My best case scenario was the rovers to find a little more than they did.
Well, they're sending the drone there
to
they got an aeronautical element going.
And I'm not saying that's great technology to get at, but when you go there, what more are you going to do?
Exactly.
Right? And again, you got to bring all your there's no resources. You got to bring all your resources with you. So why do we want to go inhabit the Mars if there's no resources there?
Because it's cool. That's cool. That's it.
It needs to be more than that.
Does it, Kurt?
It does.
So would you rather see asteroids? Because that's where I'm excited about is asteroid mining.
We have looked at some technology about landing on asteroids and doing things on asteroids, and it's very cool. And and that all gets back to Armageddon.
Yeah.
And
ridiculous movie.
No, but I mean, fun.
Yeah, it is fun.
The whole idea was fun. It was not practical.
Because that's what you want to do. Turn
fun.
One giant object heading to Earth into thousands, right?
That's correct.
Yeah.
Well, and you'd be in charge of training.
That's right.
Bruce Willis and his team, right?
Yeah.
You'd have to deal with the oil riggers.
Ben Affleck giving you attitude.
NASA actually gave that film crew access to the Neutral Buoyancy Lab. Some of the video that was done for that movie was actually done in the Neutral Buoyancy Lab. Funnest time any of those guys ever had doing work was for them to bring in their toys and them actually being on video, and they actually got credits after in the movie.
That's cool.
NASA Neutral Buoyancy Lab, and we actually and the guys loved it because film crews they seem to have an endless amount of money.
Yeah.
every lunch was catered.
Oh, yeah.
You know, overtime was full paid, you know, and it was like, oh, cool.
That's a
Let's
sweet deal.
go to work today, you
Yeah.
know. Normally it's like get your cup of coffee and get in the water. No, you get lunch and
Yeah.
breakfast and
You get
coffee.
to hang out with Liv
and-
Tyler.
Yeah, and you actually get to hang out with the actors,
Yeah.
you know, and that was, they thought that was the best thing. And
That's amazing.
I think there's only been 2 movies. The other one was, I think it was Cowboys.
Oh, Cowboys in Space.
Yeah, where
that
it
was a great movie with
yeah.
Tommy Lee Jones.
Yes,
and okay.
They
Keith
also
Urso.
they also did some filming in the Neutral Buoyancy Lab or at NASA for different areas in the film.
That makes sense. That was an underrated movie, by the way. That was a very
is.
sweet, underrated movie. That was very nice. Well, just one more question for you, and then we gotta probably wrap it up here. We're doing
Okay.
good on time here. But what is your go-to? Okay, Hollywood, you figured it out. You got it right. Other than Armageddon and their impeccable accuracy
Yeah, Mars was one of the best movies, and they also had some astronauts involved.
with Matt Damon.
Yeah,
Okay.
in Mars.
Okay.
One that they actually had a lot of interaction with NASA and astronauts was Gravity. Another great, I mean, it was all filmed in space.
Yeah.
And it was, in my opinion, one of the worst movies ever made from a technical aspect.
Right.
Because they were...
Well, it wasn't filmed in space. It was filmed on Earth about space.
Correct.
Okay. I just wanted to clear that up for the
and-
audience. They're like, damn, Sandra Bullock went to space, yo.
She didn't go to space,
Okay.
but everything they were doing...
Was shot outside in space.
No, I'm just saying everything that they were doing, they weren't following what it would be like in space.
Gotcha.
You saw Sandra Bullock skinny into a spacesuit
Yeah.
in shorts and a t-shirt.
Mm-hmm.
It doesn't work that way.
No?
You know, they wear this long john outfit that's full of tubing that actually provides cooling agent to cool their bodies. Because if you actually just got in a spacesuit without this thing on, you would cook. Your
Interesting.
body temperature would
heat up.
would
yeah.
heat up, and there's no way to cool it down.
Wow.
So you saw her skimming out in shorts and a t-shirt, and you're going, that's really cool. And
Yeah.
and she's ready to go in like 2 minutes, right? And anytime an astronaut goes into a spacewalk, he spends at least 4 hours in a prep and an oxygen environment system
Damn.
to prep before he goes out the door, because once he goes out the door, it's a harsher environment, and
Yeah.
his body needs to be ready for it. And just those kind of things. And then I believe that was the one where they pulled out the fire extinguisher and started scooting around.
That was it.
That's a fantasy. So,
No? Ah. Not going to happen?
so NASA spends a bunch of money on cryogenic fuels to the astronauts. They all fly with, it's called a SAFER, but it's a emergency backpack.
Okay.
If they get separated from the vehicle,
Right.
they've got one
Oh,
shot.
it's like your little jetpack.
They got
Okay.
but it's all cold fuels.
Right.
So there's no,
Yeah. Yeah, because nothing ignites in space, right?
Right. So it's all cold fuels, and they have about 10 seconds of fuel.
Better make it count.
Right.
Yeah.
And so
Unlike
they
George
actually
George Clooney had triple that. He
another
was a little cavalier with it.
another great test facility at NASA is their virtual reality lab, which is goggles 3D.
Yeah.
And they have a model of the entire space station and the shuttle, and they simulate sending a guy. He got separated from the vehicle and he needs to get back to it. So they give him a rate and a spin, how quickly he's separating from the space station.
Oh, God.
And he needs, having 10 bursts of propellant, he needs to stop his spin, rotate his body so that he's looking back at the vehicle, and then spend all the rest of your fuel to get some kind of velocity going back to that vehicle.
Have you ever done it?
I've done it in the simulator.
Okay.
Yes.
Yeah, well, of course, yeah.
It's nearly impossible to
I
do.
bet. Because then you
right?
go and you just miss the damn thing.
Right.
Or you skip off of it, right?
Or that's just it. Once you get back, and they did this in a lot of the movies where, they're buzzing around outside and they're just flying from one module to the next, and it's like that never happens. Everything is he's got a safety tether on, and he's never allowed to let go with both hands.
Okay.
Right.
That's
There's always a hand over hand protocol, and you never let go of the first one before you grab onto the second one.
It's an old wingman's motto. The people that used to walk on the wings on biplanes, that's
Sure.
the motto. Never let go of something until you have a hold of something else.
Correct. And you have to live by it. But in these movies, they're just flying
Yeah.
from module to module, and they're not tethered or anything. And,
Yeah, it took a bit of
and they
few
have all
liberties
these backpacks that zoom around. And
Yeah, with infinite number of fuel.
Sure,
Yeah.
sure. It's
That's
always,
the number one
What about
fear.
the Matt Damon thing in Mars whenever he poked a hole in his suit and used it like an Iron Man, remember?
Yeah,
and like a
Iron Man.
jetpack?
doesn't work that
Not
way
it?
either.
Damn it.
You know?
This is awesome.
But he has, like I said, the spacesuit is a spaceship
Yeah.
in itself. So he has
So it's pressurized.
but he has limited air,
Yeah.
limited environment.
Not enough to do what he did.
And you don't want to be doing that
That's where
with
they
your
lost you?
breathing air.
Yeah.
You know?
That's where they lost him. They had in the whole movie. That was it.
And they're not controlling that. And yeah, it's okay. But when they launched off of Mars in the movie Mars, that was so awesome.
That was awesome.
The way that
jetted all the-
they got rid of everything,
Yeah.
and they're using a parachute to cover the vehicle to give it some minimal amount of drag as it's launching.
Yeah, because wind resistance is a lot different because it has no atmosphere, right? Or
It has some.
hella little atmosphere.
Yeah,
Nothing like we are compared to.
Correct, nothing at all, but it still has drag, and
Yeah.
you want to minimize that when you're launching. Otherwise, it's just keeping you down.
So you took the weight out from the panels, but then that exposed a bunch of crevices where oxygen or air could be captured and create drag. So you want to
took the whole top off the
Yeah.
capsule, as I remember. So
Yeah.
it was like all that was just going to act as a wind drag,
right.
and your initial ascent until you get into true vacuum.
Damn, that's cool.
And the other one, the only bad thing about Mars, or I should say, the worst thing was the whole premise for the movie. You had to give him license. How did he get stuck on Mars?
Yes.
There was some like windstorm, right? There ain't no wind on Mars.
Nope.
So I mean,
Damn. Straight out the gate.
straight out. I mean, but in order to make the story or to set the story, they had to create an incident.
An issue, yeah.
And that was the incident. And we're sitting there going, yeah, that ain't going to happen.
Yeah.
But I went to Gravity with a couple of very good friends of mine that are, very techie, NASA space guys.
Mm-hmm.
And while we were there, there was actually an astronaut we trained was there with his wife watching the movie.
Oh, cool.
We come out of the movie and we're both, talking with one another and dissing the movie.
Oh, yeah.
As you're coming out. He comes walking down the aisle behind us with his wife, arm in arm, and all of a sudden he starts putting his finger in his mouth going, you gag,
puking it.
because how bad the movie
Yeah.
was gagging. And his wife is sitting there beating on him.
It was her idea.
We're in public. Stop doing that. It was hilarious. Hilarious.
That is awesome.
But it was so true. Even the astronauts are sitting there going, that's just not real. I mean, it's cool as you're making this look. And you got to give them some license.
Sure.
But
Yeah.
we gave Gravity like a half star for
Okay.
pulling off technical reality. And then
That half star was
don't
only because it had a sexy Sandra Bullock in it, too.
That's a true statement.
Yeah, I took my girlfriend to see that at the time, and she did not understand why I was not thrilled with that movie. Yeah, she said, wasn't that great? It's like,
Yes.
yeah.
I'm upset.
And they created this China space station out of nowhere.
Yeah, they
Where's that
disappeared.
one? Where's
Yeah,
that
that's
one?
fine.
Oh, that's-
Well, it's like in Cowboys. They had the Space Cowboys. They had that Russian thing that had a bunch of nukes on it that was falling back to Earth, and that
Sure.
was problematic.
Yeah. Yeah.
There's a bunch of stuff up there we don't know about.
We gotta pretend to make the reality happen. That's right.
Absolutely. Thank you so much, man. I really appreciate
Welcome.
this. This was awesome. We'll definitely do it again. You're my NASA consult now. My
Oh,
Boeing
there we
NASA
go.
consult. So, Patrick, thank you so much, dude. Do you have anything additional or anything you'd like to say?
Thank you. No, I appreciate it. This was
It's been fun.
fantastically interesting.
Been fun talking.
Absolutely. Well, you're wonderful. You're always invited back anytime. Listeners, thank you guys so much for joining us. Please just check us out on the Instagram there at Expanding Reality Podcast. Facebook there for as long as I keep that up. YouTube, there will be a video of this up. And then be good to one another. Get out of the left-hand lane. Just do something nice for somebody else. And go watch Gravity and just pick it apart. And that'll be fun. Curt, Patrick, thank you guys so much. We really appreciate it. Thank you.
It's been great being here. Thank you.
Yes, sir.
Thank you.